The last time we have been discussing about the Hohmann and bielliptic transfer. So, we will try to complete it this time. So, last time as we developed for the Hohmann transfer, the change in velocity delta v divided by v I is given by this equation, which I have numbered as 1, and for the bielliptic transfer similarly I got the equation delta v by v I as this one, where n is the n we choose as R f by R I, where R f is the radius of the final orbit and I is the radius of the initial orbit, and n star was chosen as the R b by R I, means this is the intermediate orbit, where R b was the radius of intermediate orbit. So, now we will utilize these two equations to make the graph. Okay. So, if we plot delta v on this x and n on this x, so for the Hohmann transfer, that is using equation 1, we will get a curve which will look like and this maximum value also we found it theoretically, and this value was around 15.58. So, exact value for this we calculated exact the more precise value, and that value turned out to be 15.58, 15.58176. So, we are approximating this using 15.58, and for a circular orbit of radius r e, that is equal to the radius of earth. So, suppose a satellite is moving in a circular orbit whose radius is just as the radius of the earth, and replace earth by a point mass of the same mass as that of the earth, then you can get the value of this delta v. So, here the r earth value, this will be around 6378.1363 kilometers. Okay. The value for mu for the earth is 398600 kilometer cubic second square. So, this constitutes your initial radius. Now, with this initial radius r I, we can calculate V I equal to mu by r I under root. So, 398600 divided by 36378.1363, and this gives you velocity in kilometer per second. So, this will turn out to be around 7.90536 kilometers per second. Okay. So, if you choose n, which is nothing but equal to the radius of the final orbit divided by radius of the initial orbit, okay, is equal to 15.58176. Then you can calculate delta v according to equation 1, delta v, calculate it. So, delta V by V I, what you get it is 0.536258 by inserting this value of n. Okay. So, insert in the equation number 1, insert it in equation 1, and therefore, you get this quantity. Okay. So, if delta V is known, V I is known from this place. So, therefore, delta V will be 0.536258 times 7.90536. Okay, and this will turn out to be around 4.23 kilometer per second. So, this is the change in velocity required, total change in velocity, or the total impulse required, and this we have calculated earlier and connected this with the amount of propellant that will be consumed. Okay, and theoretically we developed that equation. So, therefore, corresponding to this value turns out to be 4.23, and this we are plotting in kilometer per second. Similarly, we can put here say this value to be the value of n to be 3. So, this will turn out to be around 3.11. Okay, and this we are doing for Hohmann transfer. This is for Hohmann transfer. Okay, so, you can see that once these equations are available. So, without much problem we are able to draw this curve, and this can be easily done on a computer. So, remember that we are choosing the radius of the orbit to be the same as the radius of the earth. So, you have the earth here. So, you can assume that the earth is there, but at this is suppose this is the radius of the earth, this is r e. Okay. So, obviously, if earth is there, then you cannot move it, but this earth can be assumed to be a point mass here of m, and then some satellite is moving in the same radius. Okay. So, this is the m earth, mass of the earth, and mu is given to you. This is the value of the mu for the earth. This radius is available here. Now, based on this we have got this result. Okay. So, from here onwards we can work further to calculate various values. Okay, the next question is what will happen to this bielliptic transfer. Now, bielliptic transfer we have another parameter appearing, which is n star. This is our n star. Okay. So, obviously, we will get multiple curves in the case of bielliptic transfer, because n star is present. We can choose different values of n star, and then we can vary the value of n and plot the curve. So, for different values of n star, obviously, then we get a number of curves as we value the change the value of n star. So, using equation 2, that is this equation, again we can work out for the bielliptic transfer case. Okay. So, plotting this, this is n star equal to 15.58176. Okay. So, this green line is referring to the bielliptic transfer. So, n star means the intermediate orbit. So, radius of the intermediate orbit, if it is 15 times the 15.58176 times the initial orbit, radius of the initial orbit, then we get this curve, and on this side this starts from here and then goes into this direction. Okay. If we increase the value of n star further, so we get a different curve. Okay. Similarly, if we take the value of n star to be 60, so we get another curve. And if we choose n star to be infinity, this curve results. This is little shifted, this is not exactly in the same point. So, here in the 15.58 point is there. So, we will earlier we have found out the crossing point for the Hohmann transfer curve and the bielliptic transfer curve, and this point it turned out to be 11.94. Okay. So, for n equal to infinity, this curve cuts here in this point, and thereafter the other curve with other parameters, as for example, this for 60 n star equal to 60, this also it does not pass through this point, rather it goes through right of the this black line which is coming from here to here. So, this is our bielliptic transfer. This is bielliptic transfer, and this is the black one which is shown here, this is the Hohmann transfer. Okay. So, the Hohmann transfer it starts from here and it goes into this direction, while the bielliptic transfer all of them it for the smaller value of n it starts here for a small, as we take the value of n star equal to infinity. So, it is starting here in this place, okay, and as we change the value of n, so it is progressing in this direction. Similarly, this one has resulted for n star is equal to 15.58, and as we change the value of n gradually from 0 onwards. So, this point is 0. So, as we change it from 0 onwards. So, similarly, we will get the result for this curve. So, it comes here, it cuts near 15.58 and then goes in this direction. Okay. So, overall this cutting points we can show like this is our Hohmann transfer, and this is the bielliptic transfer for n star equal to infinity. and this point where it cut on the x axis, this point was our 11.94 and where it is cutting, this point is 15.58. Okay, so you can see the difference in these 2 points. This green line is crossing the red line and cutting it here in this point, and thereafter it is moving in this direction. So, for all other values of n star, okay, so the lines will lie between this n star equal to infinity, this is for n star equal to infinity and this is for n star is equal to 15.58. So, all other lines must lie between these two ranges. Okay, so, wherever the two curves are cutting each other, that can be easily solved by using these two equations. We have the first Hohmann transfer equation and this is the second bielliptic transfer. So, this curve, the cutting point we are defining for the Hohmann transfer and n star equal to infinity. So, in that case in the bielliptic transfer equation we have to put n star equal to infinity and this equation then gets simplified and then these two must be equated to solve for this cutting point which I have shown here in this place. Okay. Okay, so, from this bielliptic transfer if we put n star is equal to infinity. So, this will result in delta V by V I. This quantity you can see from here, this is 2 divided by 1 by n star plus 1 under root minus 1. This is 2 divided by n star times 1 by Okay, now in this equation put n star equal to infinity. So, as we put this term becomes equal to 0. Okay, here 1 by n star this will become equal to 0. So, put n star equal to infinity. Okay, so, this becomes the first term becomes 2 under root minus 1. This whole term will turn out to be 0 and here we have 1 by n under root and here n is putting n star equal to infinity, this goes to 0 and what you get here under root 2 minus 1. So, this becomes under root 2 minus 1 times 1 plus 1 by n under root. So, delta V by V I, okay, and this is for bielliptic n star equal to infinity. So, what we are trying to find it out that when this bielliptic transfer and the Hohmann transfer they will equalize, and therefore, you need to solve these two equations delta V by V I root 2 minus 1 this is equal to 1 minus 1 by n times 2 n by n plus 1 under root. Okay, how to get this equation alternatively, we will look into that later on. Right now, we just concentrate on finding out the cutting point, which is the point here, or the in this figure we have shown this point, we are trying to find it right now. So, we can solve it. The simplification is little longer, but some of the steps can be carried out here. So, what we can do, we can expand this term here on the right hand side. So, this I will write on the left hand side, this particular term which is appearing on the right hand side. So, this is 2 n by, okay, this term also we need to expand. So, this is root 2 plus root 2 by root n minus 1 by n under root. Okay, and now expand this. So, this becomes 2 n by n plus 1 under root minus 2 by n times n plus 1 under root plus 1 by n under root minus 1. So, these two terms, this and this, they cancel out. And after little bit of simplification, you can write them as under root n plus 1 minus root 2 equal to okay. So, this equation can be reduced to this equation, it is easier doing it, but I am just skipping those steps here. Okay. This can be further simplified, as you can see from this place, the RHS, this is nothing but n minus 1 divided by n. So, this gets reduced to n minus 1 divided by n plus 1 under root. Okay. So, therefore, this equation then you can write as this particular equation, this can be written as n times n plus 1 under root. So, what we are doing, this term we are, the term in the denominator we are taking on the left hand side. So, this term under root n gets multiplied by this one. One minus under root 2 times n plus 1 under root equal to n minus 1. And because this is containing the square root sign here, so we need to eliminate it. So, we need to square both the sides. So, squaring both the sides, n minus 1 ka square. Yes. So, this is n minus 1 square. Now, this can be further simplified, and after some simplification, this can be reduced to 3 n minus under root 2 n plus 1 minus under root 2 okay, but still this equation it contains the square root sign for n. So, we need to eliminate this square root sign again. So, again we do the same process, of squaring by rearranging the terms. So, after this rearrangement you can find it out that the terms will appear as rearranging and squaring, rearranging and squaring. This leads to this equation and simplify it further. So, further simplification, this will result in a cubic equation and you can solve it on MATLAB, and this will give you n equal to 11.93876, which I have approximated as 11.94. Okay. So, this is the solution that we got last time. We have used this last time here in this place. This is the cutting point for the Hohmann transfer and the bielliptic transfer for the limiting case. This is the limiting case where n star equal to infinity. So, the intermediate orbit is at infinity. So, in this case we are the bielliptic transfer and the Hohmann transfer, they get equalized for the value of n equal to 11.94, that is the R f by R I equal to n equal to 11.94. This is the final radius of the final orbit by radius of the initial orbit. Okay, so, this completes our discussion for the Hohmann and the bielliptic transfer. Now, what I told that the relation that we got for the limiting case of bielliptic transfer, this is the limiting case of bielliptic transfer. Okay. So, this equation can be derived alternatively. So, in the bielliptic transfer what we have done, this is the initial orbit given whose radius is R I, and this is the final orbit given whose radius is R f. So, in bielliptic transfer we transfer from point A to point B, okay, and here the impulse delta V A was given, and then again the impulse here delta V was given, B V was given, and then it is transferred to this point in an elliptic orbit. This is the elliptic orbit. So, we can write this as the eccentricity of this orbit to be E t 1 and eccentricity of this orbit to be E t 2. Okay. So, if we are transferring from this point to the infinity, so you can utilize the Hohmann transfer relationship to find out this result. So, our equation for the Hohmann transfer is this is the equation given to us. So, using this equation number 1. So, if we put in this moment transfer n equal to infinity, suppose we are here in this place and we are trying to transfer it to infinity. Okay. So, if we put n equal to infinity in this point, so the result that we get will be delta v by v I, this is equal to n equal to infinity. So, this term vanishes and here if we divide this is, then we get root 2. So, this is root 2 and again this term vanishes and we get minus 1. So, therefore, we can write delta V A is equal to V I times root 2 minus 1. Now, you need to get back into this point. So, if you look back from this point, suppose that you need to transfer from this point to infinity. So, still you will utilize the same equation, only thing here instead of V initial it will be V final. So, this is equivalent to that you need to escape from infinity and come to this point. So, using this equation again you can write the result. So, delta V B by V final, this will be equal to root 2 minus 1 if n equal to infinity is inserted in equation 1. Okay. So, this is our, so delta V B becomes now add these two equations. Adding 3 and 4, this gives you delta V is equal to delta V A plus delta V B. So, why delta V? It is written in terms of delta V, because you need impulse to escape from this, but as a whole we are calculating the energy required to get into this circular orbit. Okay, and that you can put here another notation also, but I am just putting here delta V. Okay, so, delta V A plus delta V B, this turns out to be minus root 2 minus 1 V I plus root 2 minus 1 V F, root 2 minus 1 times V F. Now, V F is mu by R F under root, because it is in a circular orbit, and this you can write as R F divided by R I, and mu by R I under root is nothing but V I, and R F by R I is nothing but n. So, this is what we get, and therefore, delta V equal to root 2 minus 1 V I plus under root n times root 2 minus 1, taking root 2 common, root 2 minus 1 common, what we get here 1 plus 1 by n under root times V I, or delta V by V I equal to root 2 minus 1. This is what we got using the bielliptic equation also. So, we see that the same result can be obtained in a multiple of way, but what our objective was here to find out how we are getting this point 11.94, where the this black curve for the bielliptic transfer and black curve for the Hohmann transfer, they are intersecting, which is the point 11.94. We take a simple problem, but it will effectively demonstrate the concept that we have been developing till now. So, in this problem we are given an initial orbit whose radius is r I, and the satellite is to be transferred from the initial to the final orbit, whose radius is r f. Okay, using Hohmann transfer. Okay, so, this is point A and this is point B. Now, all the informations are not given. So, r I is given to be 7000 kilometer. Okay. R f is not given, but instead of r f, what is given is your period of the final orbit, which is circular in this case. So, this is the orbit whose radius is r f and its period is given. So, we can calculate it. So, period will be given as t equal to 2 pi a q by mu under root, and this is 12 hours. So, 12 times 3600 equal to 2 pi a q by mu under root, and mu we know this quantity is 398600 kilometer cubic per second square. So, once we insert this value into this equation, it can be solved for A, and A will be nothing but equal to A equal to R f in this case. So, A equal to R f, if we solve it, finally we get 26610.235 kilometers. So, now you have the initial or radius is given and final radius is also known to you. So, this quantity we have just now found out, this is 26610.235 kilometer. Okay. And therefore, eccentricity of this transfer orbit can be calculated, which is shown by the blue line here. So, eccentricity of the transfer orbit, this will be given by r f minus r I divided by r f plus r I. Okay, so, this is 26610.235 minus 7000. Okay, and this value turns out to be around 0.58344602. Now, velocity in the initial circular orbit. So, V A in the circular orbit, which is shown by C here. Okay. To indicate the circular orbit. So, this can be written as mu by r I under root. So, mu is nothing but 398600 and divided by 7000 under root. Now, we need to send this into the elliptic orbit. Okay. So, for that V A in the elliptic orbit, it can be written as 2 by r A minus 1 by A transfer orbit, which is the elliptic orbit, semi major axis of the transfer orbit. Okay. So, inserting the values, and A will turn out to be 16,805.118. So, A transfer orbit, this simply you can write as 7000 plus 26,610.235, which is the radius of the initial orbit, radius of the final orbit divided by 2. This will be 16 point R I plus what we have taken R f plus R I divided by 2. So, this was 26. So, this will turn out to be around 16,805.118 kilometers, and this is the result we are inserting here, and this gives you the value 9495629. Okay. Once you have, so from here how much impulse is required, that you can calculate how much velocity change is required. Now, the satellite will go into this position. So, in this elliptic orbit you need to calculate the velocity of the satellite, and we are doing it from the first principle instead of using the equations. So, V b in elliptical orbit, again this can be written as mu by R b minus 1 by A transfer under root, and R b is here 26,610.235 and A t is 16,805.118 kilometers, this also kilometers. Mu is same as given here. So, inserting these values you can calculate this, and this will turn out to be so V b in the elliptical orbit, this is 2.498 kilometer per second. Now, at this point here we give the delta V a impulse, and here we need to give delta V b impulse. Okay. So, you need to change the velocity here in this point. So, you need to find the velocity in the circular orbit at B. So, V b in the circular orbit, this will be mu by R f under root. So, mu is 398,600 and radius of the final orbit is 26610.235. Okay, so, we have calculated the velocity at these points in the circular as well as in the elliptic orbit. Now, it is easy to calculate how much impulse will be required. So, how much change in velocity is required is given by delta V a plus delta V b. So, this is 9 point in the elliptic orbit at point A, the value we have got this is 9.495629, and minus we have to subtract the value that we got in the elliptic orbit at point A. So, this was in the elliptic orbit, and in the circular orbit we have got as 7.54. So, this is in elliptic orbit, okay. And the circular orbit we have got which is 7.54605. So, insert this value also here. and then delta v similarly we need to find out, subtract from the velocity in the circular orbit minus the velocity in the elliptical orbit at point B. Okay, and this value right now we have derived, and this is 3.87. Okay, minus 2.498. So, we can delete this. So, this will give the value, this is 3.3218. Okay, so, this is the total impulse required or the total velocity change required that we need to provide. Now, once you know this velocity, so it is easier to calculate the amount of propellant required by the equations we have developed earlier. So, this very simple problem gives a lot of information about the discussion we have made earlier, and it clarifies all the points numerically. Okay, now, the question is it possible to achieve fuel economy? Is it possible to achieve fuel economy by elliptic transfer, which is 3 impulse transfer? So, naturally we have discussed about the bielliptic transfer just before. So, can we say anything about this from the graph we made? So, in this region, as earlier we have discussed, before the point 11 point, this point is 15.58 and this point is 11.94. So, before this point Hohmann transfer is best, and after 15.58 undoubtedly bielliptic transfer is the best. In mid between it remains doubtful. Okay, where the curves are passing, that you have to see, and that best can be done using the numerical calculation. So, in this region I am sure that the Hohmann transfer is best, in this region the bielliptic transfer is best. So, what we can state that if R f by R I this is greater than 15, then only I can be sure that bielliptic transfer will be the best. Okay. But in that case, as you can see, the R f will be 7000 times 15. So, this is the minimum value of R f required. One lakh 5,000 kilometers. So, this is your R f minimum. Okay, for transferring in such an orbit, you will see that the amount of time required will be very high, okay, as compared to the smaller orbit that we have taken for the transfer here. So, for a smaller orbit our Hohmann transfer is good, but if the radius of the orbit increases, and in this case you can see that how large it is becoming. So, then only your bielliptic transfer is becoming more useful. So, here in this case you have the final orbit. So, the final orbit radius need to be therefore, bielliptic transfer is not applicable. So, again look into this curve, this is not very clear, but still here this has got little blurred, but in this region definitely you can see that till the point 11.94 the Hohmann transfer curve it lies below the bielliptic transfer curve, which is here the bielliptic transfer curve for the intermediate radius of n star equal to infinity, and this is for n star equal to 15.58176. So, in this region where the n is less than 11.94, delta V is coming lesser than the value of the bielliptic transfer, okay, which is corresponding to n star equal to infinity, and obviously if you try to choose for n star equal to infinity. So, you know the how much time consuming it will become. If n star is infinity means virtually infinite time you require to transfer. Okay. So, this is not possible. So, we cannot consider of the bielliptic transfer. So, ultimately the limit remains here in this point that we go for this transfer, which is the Hohmann transfer, and rest others you can consider here. So, this is obviously eliminated, this case is eliminated, and we can look for the other cases and find out for the intermediate things like n star equal to 15.58 or n star equal to 40 or n star equal to 60, which is going to be more efficient as we go above the 15.58 point, but this is obviously not useful. Okay. So, from here what we conclude that our Hohmann transfer is best for our satellite transfer from one orbit to another orbit, as we do in our usual cases for the Earth satellite, where the satellite may be in the low Earth orbit or the may be in the GTO, which is called the geosynchronous transfer orbit. It has to be transferred into the geosynchronous orbit. So, if that kind of transfer is to be done, then you naturally you go for the Hohmann transfer, and this whatever we are looking here into this. So, n star equal to 40 and other values. So, that may be useful for the interplanetary transfer once we are going from one just planet to another planet. So, at that time these orbits may be useful, otherwise in the present context where we are dealing with the Earth, these orbits the bielliptic transfer are not useful. Okay. So, bielliptic transfer will be not useful until unless we have the final orbit radius much larger than the initial orbit radius. Say in this case we took the 7,000 kilometer and then 15 times more means 1,05,000 kilometer. So, this type of cases will happen only in the case once you are going to transfer the satellite from Earth to Moon. Okay, only it is a possible, the nearest possibility is. otherwise it is not possible. So, you want to raise the orbit. So, how to raise it? So, this is the solution here. Okay, so, we stop here and we continue with the discussion next time. So, we will go into the trajectory transfer further and looking into rendezvous problems and other things. Thank you very much.